as a PhD scholar in IIT Delhi. Today I'm going to present my work on error immune quantum communication, which is done in collaboration with Professor Veera Vishankar. This is the brief outline of today's talk. So let's get started with the motivation of the work. So we want in our every day-to-day activity, every task requires the transfer of information. So that is this is a task of a primordial importance. But the important question is how to transfer information. So information is usually transferred by encoding in a state of a system. However, after encoding of information, when a state travels from one place to another, its interaction with the environment is inevitable. Due to this interaction, the state of the system changes, which results in the change in the information carried by it. That is, the task which we have taken in hand is compromised. The main question is now what to do. So several way outs have already been proposed in terms of quantum error correcting codes and decoherence free subspaces. These techniques either protect a state from being corrupted by the noisy operations, or these techniques recover the original state from the noisy state. However, all these techniques use entanglement as a resource. That is, the information is encoded in a multipartite entangled state. After retrieval of after getting this uncorrupted state, the main question is how to retrieve information, and for that, complete tomography of the state is required. Since the information was being encoded in entangled state, the complete tomography demands large number of copies of the entangled state. However, the generation of entangled state is a difficult task in itself because it is a second order nonlinear process. Therefore, we ask the question. So the question is, can information be encoded in a way that we can transfer information in an error immune manner with little or no usage of such costly resources such as entanglement? Fortunately, the answer to this question is in the affirmative and is given by the scaling law. So let's get inherited with the idea how this scaling helps us um, in solving this particular problem. So scaling laws provide us with multilinear quantities that remain invariant for a particular set of phase space trajectory. We can understand this statement with the example. So let's consider the example of a Kepler's third law. So Kepler's third law that curve of the orbital period is proportional to the cube of the size of orbit. So what it wants to say, when we go from one orbit to another orbit, the size of the orbit is being rescaled. And in accordance with the size of the orbit, the orbital period is also. What we want to do, we want to use this idea for rescaling and want to look for the operators whose expectation values are simply being rescaled. And then want to use those operators and the expectation value of those operators to encode information so that it can be transferred in an error immune manner. So let's get started with the formalism of the work. So any noisy channel, mathematically it is represented by the quantum operation E. And these quantum operations are so one way to represent these operators via operator representation. So where this EK are called the cross operators which satisfy this particular condition. Now let's assume that this rho is the state which is being used to transfer the information. And if that is so, after passing through noisy channel, this rho changes to rho prime through this noisy operation, which is shown here. Now, the idea is to look at those operators which are getting rescaled under the noisy evolution of the state. So if we look at the Heisenberg picture, so we are talking about this particular kind of operator. So what is happening? The expectation value of this operator O alpha for the noisy state is simply rescaled by a factor lambda alpha from the expectation value of the same operator over the original state in which information was encoded. So if somehow we can get rid of this factor lambda alpha, then we will have the corresponding quantity which remain invariant under this noisy evolution of a state. And so we will have an invariant and we can encode information in that invariant so that it can be transferred in an immune manner. Now this constraint put up a constraint on this operator of this kind. Okay, so given this thing, we now consider a function of expectation value as we have discussed. So this function of the left hand side of the equation, in this expectation values are taken over the noisy state, and in the right hand side we are taking the expectation value over the original uncorrupted state. So we are able to see that the two are related with each other. And now if we put a constraint over this prefactor that it is equal to 1, the two quantities will be simply equal to each other. Therefore, if we have encoded information in some operator with given state O, that even after the noisy evolution of the state, the corresponding information we simply retrieve. That is, this quantity remains invariant, and so the information encoded in it. Now, this quantity in itself has a very complex structure. Therefore, we categorize these invariants into three different families. So let's start with the first family. So in the first family, we assume that the scaling factor lambda is simply 1. So what we want to say that these operators do not change noise evolution the of the operators, that is they remain invariant, and so the information encoded in them. So all such invariants in with the scale, so expectation value of all such operators which are not uh, changing at all under the noisy evolution of a state are belong to the first family. Till now, we haven't made any assumption about this cross operator. However, if you consider special case in which this cross operator are scaled unitary operators, that is, we can write EK as some square root of a PK, UK, where UK is a unitary transformation and PK is the corresponding associated weight. So, noisy channel, this condition is trivially satisfied by all the operators that commute with the all these unitary operators. Given this information, we will build upon, we can get invariants for different noisy channels of our system. Now, this particular kind of invariant have already been obtained in this work, and there it is being used to recognize steady state structures. Now, going over to the second family, which is of utmost importance, as this family provides us with a large number of invariants in which we can encode our information and therefore can be transferred in an error-immune manner. So, for this family, we consider a pair of operators such that they change in a commensurate manner under the noisy evolution. That is, the expectation value of operator O1 with the noisy state changes by the same factor lambda as the expectation value of operator O2 for the same noisy state. And if that is so, the ratio of the two remains invariant. That is, if we encode information in these quantities, that will remain invariant. Now, going over to the third family. So, in third family, we elevate this condition of change in the operators in a commensurate manner. However, we consider all such kind of operators which can be 2 or more than 2 such that the corresponding product is remaining invariant. So all such invariants belong to the third family. So after building upon this formalism, we now move to the application part, in which we obtain many invariants for various noisy channels for an n-level system, which is a QNet. However, before getting to that point, let's get started with some basic knowledge which will be required. Now, whenever we have an n-level system, the corresponding operator sits in an n-square dimensional space. So therefore, we need to define n-square basis operator for the same, which are defined as this. So here we have defined three set of operators, in which this dk is a diagonal operators which are which are n in number. However, this SKL and AKL both are off diagonal operators which are n choose to in number. This SKL are the symmetric operators, whereas this AKL are antisymmetric operators. However, for future use, we define a more general diagonal operator, which is the difference between the two basis diagonal operators. So we will use this S, A and capital D operators for future use. Yeah. Now going to the application part, we first consider the generalized polychannel. So generalized polychannel is a higher dimensional generalization of a polychannel of a qubit. So as we know, the polychannel was described by all the possible combinations of this X and Z operator. In the similar way, the generalized polychannel is defined in the same way, where this X is higher dimensional generalization of a sigma X operator, and this Z is higher dimensional generalization of the sigma Z operator, which is corresponding to the flip and the phase errors. Therefore, a state after passing through generalized polychannel changes accordingly this equation. we do not have but we do not have any invariant for this general channel. However, if we consider special cases of this generalized polychannel, we have a large number of invariants. So let's get started with special cases of this generalized polychannel. So we first consider the generalized flip error, which is a higher dimensional generalization of a bit flip error. uh, Please mind that here we have n cross operators which are acting probabilistically over the state. And what are the probabilities? We do not have put any constraint on them. No, under such channels, we obtain n minus 1 invariants from the first family, since these are all unitary operator and they commute with each of them. Therefore, expectation value of these operators remain invariant. Similarly, we have n minus 1 square of independent invariants from the second family. Thus, this generalized flip error provides us with n minus 1 independent invariant quantities. That is, we can send n minus 1 pieces of information without any error using a QNet. Similarly, if we consider generalized phase error, which is a higher dimensional generalization of the phase flip error, again we have n minus 1 invariant from the first family and n minus 1 whole square of the invariant from the second family. Thus having in total n minus 1 independent invariant. Similarly, considering generalized combined flip and phase error, again we have n minus 1 invariant from the first family and n minus 1 whole square invariant from the first family. So this simply reflects the fact that we are having very restricted number of invariants from the first family, which are simply linear in n. However, the second family provides us invariants which are quadratic in number. Okay, so all these three channels were very special cases of the generalized polychannel. Now we move on to the more general and a practical channel, which is called the depolarizing channel. So in depolarizing channel, any error from these three or any combination of them can corrupt the state. Therefore, the generalized polychannel the only difference between generalized polychannel and depolarizing channel is that in generalized polychannel, all the probabilities are different and arbitrary. However, in depolarizing channel, all the errors commence with the same probability. Now we do not have any invariant from the first family, whereas we have almost all the pieces of information from the second family. So we have almost n square minus 2 independent invariants from the second family. Now moving over to the dephasing channel. Again, this dephasing channel, now dephasing is like any arbitrary phase state can acquire. For the same channel, we have n minus 1 independent invariants from the first family. However, we have only n choose 2 invariants from the second family, which is giving in total n minus 1 into n plus 2 by 2 independent invariants. Next, we consider a flip error due to all possible transpositions. Now, transpositions are the kind of error in which only two of the states flip into each other while the rest are remain invariant. And since we are not constraining which two, so all possible transposition we are considering here. For such a channel, we have only one invariant from the first family, whereas the second family again provide us with a large number of invariant, though being restricted to the linear in number. Now we move on to the next channel, which is of a practical importance, is the amplitude damping channel. In this amplitude damping channel, the population between different levels is changing except only one particular level. And we are calling here it as a zero. And if that is so, the state will change accordingly. Now for this channel, we do not have any invariant from the first family, though we have a and choose two invariant from the second family and one invariant we also have from the third family. So even in the amplitude damping channel, we can transfer n choose 2 plus 1 independent pieces of error-free information. Now moving on to the generalized amplitude damping channel, again we have n choose 2 independent invariants which belongs to the second family. So we have considered a plenty of noisy channels for a QNet system using the formalism, which shows that we can encode information and we can even send information without any error and without using any costly resources such as entanglement. So I conclude my talk with this information that the first family provides us with the restricted number of invariants, whereas the second family provides us in large number of invariants, usually quadratic in number. I would like to thank Professor B. Ravishankar for his guidance and many insightful suggestions. And I also like to thank Suransh Asthana for discussion and for many useful suggestions. Thank you.